Okay, now we move on to regression in Python, linear regression in Python. And this is very straightforward actually. Here we're starting out importing needed packages. Remember what this does. If you don't put this line in there in Jupyter Notebook, then the first time you try to generate a plot, the plot doesn't show, but it shows the second time. So to make it work all the time, we're going to use this command. You already know the matplotlib um, library, pandas for your data frame. And this is what is new, SciPy. So SciPy is the package. This is a class in SciPy, which is the stats class, and it has some functions in it. And we're going to be using one of those for linear regression. So when you see SS, it's scipy.stats for statistics. So let's get started. We put in some data. It's 10 columns, 10 rows, 2 columns X and Y. And that's what this is, just a simple data set, which is linear. And first thing we want to do is to calculate correlation. And if you remember from part 2 of the class video, this is your correlation coefficient. And it's basically Zx times Zy, sum of Zx times Zy, and a normalization. And you will see how we will correct this term, which is your degree of freedom. So this is your Zx. It's x minus mean, right, divided by standard deviation. To correct for that division by n minus 1, we're going to specify degree of freedom later. But right now, using degree of freedom 1 means you're dividing by n minus 1. So whatever you put here, your standard deviation will be divided by n minus that value. So you use n minus 1 when you're working with a sample and not the population. So if you work with a sample, you use n minus 1. If you have the full population, which is very unlikely most of the time, you divide by n. So to divide by n minus 1, you set degree of freedom to 1. So this is your standard z-score. And these are the values. So we do the same thing for zy, all from the scipy.stats package. You divide by n minus 1. And now we have zx and we have zy as shown here. If you just put in x without specifying the degree of freedom, it will assume degree of freedom, the value is 0, so it's going to divide by n. And it's going to treat it like a population, so it will use this equation. Of course, you take the square root, right? Standard deviation is square root of variance. So it's going to use this equation if you don't provide a second argument. But we don't want either of these two actually. What we want is to divide by 1 instead of n minus 1. That way, in this equation, you wouldn't need n minus 1 if you already set your n. If your n minus 1 is already set up to give you 1, and that's exactly what we're going to do. So you already know it's going to divide by n minus 1 if degree of freedom is 1. So we set degree of freedom to be n minus 1 so that it divides by n minus n minus 1. This used to be 1, so it will divide by n minus 1. So now this is n minus 1, so it's going to divide by what? N minus n plus 1, which gives you 1. Right? Minus times minus gives you 1. So that's exactly what we've done here. Length of x is n. So specifying the DOF, degree of freedom, to be n minus 1 so that it divides by n minus 1. And that takes care of the normalization so that this product is going to be precisely your R value, your correlation coefficient. And if you check out Excel, you will always see R squared value when you fit a straight line, trend line. And that R squared is basically the square of correlation coefficient, and you can get that here. So R squared value is just the square of your correlation coefficient. And this equation is precisely this equation, right? Sum of zx times zy. Zx times zy, get the sum. And that's exactly how we calculate correlation coefficient, and the square of that, which is your R value. And we can plot the x and the y, and this is what it looks like. It's linear. Next thing is to actually fit the line through it, and that's we use the same scipy.stats, the linear regression function, lin regress. First value is the x, second is the y, and you get all of these for free. And of course, the most important is the slope and the intercept, right? Those are the parameters that define the equation of a straight line. Y equals mx plus b. The constants or the coefficients are the slope and the intercept. R value is your correlation coefficient. P value is the same P value we studied last week, which is, last topic, which basically quantifies the confidence you have in the model. So the lower this is, the more accurate is the use of the linear regression line to fit your data. Standard error, we're not going to get into that. And basically, we print out all of those terms using this print statement. So to use it, you have the slope, you have the intercept. Just use the equation for a straight line. Slope, which is your m, times x. We're converting it from a list to an array, because you wouldn't be able to multiply a floating point by a list, right? So that's why we convert it to an array, and we add it to the intercept, y equals mx plus b. So now you have your model prediction for any given x. Here we specified all the x's that were used in the original data, and you can plot them up, which is what we do next. So this is the result of the y from model, and we're going to scatter plot the data, do a line plot for your model prediction against x. All of this is just for labeling and legend, but this is what it looks like. So model prediction is the line, the dots are your data points, and that's what is shown here. All of those, particularly these two, just gives you this equation. And how does that work? Let's start out from the left hand side. So y equals, that's what this is, right? Y equals. Plus for a string is concatenation, right? Which means add, not add, put it next, just suppose this right next to this. So y equals, then it concatenates round. So round the slope to the nearest 4 decimal points, right? So the slope had so many zeros, is going to round it up and only show 1.046, 1.0497, because the number after that is bigger than 5. Okay, so that's what this does. It rounds it up to 4 decimal places, then converts it from float to a string so that it displays it right here. Then concatenate that with times x, so it shows times x. You want a space, right? So you put a space after the x. Then concatenate that with a sign. Now that's why you have all of this, which is Pythonic. This Pythonic expression is the same as this, right? If the intercept is greater than 0, store plus as the sign. Otherwise, store minus. The reason is because if you don't do that, the intercept doesn't come with a plus, right? If the intercept is positive, it just shows up. So if you had concatenated that directly, you would have seen 1.0497 times x, then 0.113 if this intercept was positive. So to be able to display the plus or the sign, you need to use this statement, which can be written in a Pythonic way in just one line, right? Plus if the intercept is greater than 0, else show minus. So if this is true, it gives you plus, otherwise it gives you minus and stores it into sign. And that's how this works. So this shows the legends, and that's pretty much how you get that line. We talked about this in the um, class video part 2, that correlation coefficient doesn't change if you multiply each value by a constant positive value. It doesn't change if you add a constant value to everything in the columns. If you interchange x with y, it doesn't change, and we're demonstrating that here. We're actually going to do these two together. So multiply your x, so convert it from a list to an array, multiply by constant positive value, which is 2, and also add a constant value of 7 to it, and keep y as is, and get the r value. This is what it is, exactly the same as it was originally, right? Here, this is r squared, so this is it, 0.99562, 0.99562, which is precisely what this is. So it never changed. Multiplying by a constant value, adding a constant value, no change. What if you interchange x and y? The order of the argument is x before y, so we've put y in as our x and x in as our y. And what's the r value? Same deal as before. So we just showed those properties of the correlation coefficient. This is like a practical example. You're going to learn more about this term in the course of your petroleum engineering degree, but this is interval transit time for the rock and the fluid in it. This is for the rock only. So the rock plus the fluid will give you more time, because the fluid, the velocity of sound through fluids is slower than the velocity of sound through solids. So the rock is solid, it has less time. The bulk rock plus fluid has the fluid in it in addition to the rock. So the time the sound wave spends through the rock is longer because it's slower. The fluid slows it down. That's why these numbers are greater than these numbers. And all we're doing here is to generate these data frames. And we've talked about how to generate data frames from dictionaries. First argument should always be in quotes, and that's the label of your column. Then this must be a collection of some sort. Here we're using arrays. And you do that for all the other terms, and you have this as your data frame. You can scatter plot the porosity and the matrix transit time. So this and the next column to it. No, this one, matrix transit time. So scatter plot them, it looks linear, right? So we could possibly fit a straight line through this. And we use this scipy.stats package again, porosity in the x-axis, matrix transit time on the y-axis, and we check out the slope and intercept and r value. And these are the slopes, intercept, and r values respectively. R value is high, right? It goes from 0 to 1, and from -1 to +1, right? So this is strong positive correlation. And we can write out the equation, right? Y equals mx plus c. So here is the intercept, 46.7. Slope 194, right here. We got them from this function. And this is basically the equation you can use to calculate interval transit time from porosity and vice versa, right? You can easily make porosity the subject of this equation, and you can get porosity given any matrix transit time. And now we're going to plot this equation and the data together. And that's what all of this is. And this is a little more wordy than the previous method to generate this plot because we want a better plot than this. And that is exactly what gave you the plot I used in the class. I created it from this. So I customized it. You can go through this because that's why I'm giving you this function. You can go through it when you want to create high resolution images. You use DPI 150 or more. It increases the resolution. I actually save it as 600. So it's very high resolution. So it looks nice, which is what you saw in your PowerPoint slide. So the process is pretty much the same. The important thing is you can specify the color, line style, none, meaning I don't want a line, I want dots, which is why you have red dots. If you don't specify anything by default, it's going to plot a line, which is what it does for the second with the blue line. So I don't specify ls. Marker 0, so use a circle. That's why you have a red circle. Size of the circle is 5. Label is data. For the second one, the blue line, the label is a text I create just like I showed earlier, and exactly the same thing. All right, I'm just using the intercept I got from the feet. And this is what you get. This is exactly what I discussed in class. There was one typo I extrapolated and said it will be around 72, but this is actually 46. Yes, this is the right value. Why? Because you see it doesn't go to 0. So the figure has been created so that it doesn't start from 0. So if you push this out so it starts from 0, then you will have more room to draw this line down, and the interval transit time will have dropped to 46. So these values are correct. This is just setting axis. I'm asking you to do this exercise. Instead of doing the linear regression on interval transit time versus porosity, can you do the same thing, but for interval transit time versus depth instead? Depth was the first column in the data frame, this guy. So do this against this. That's for your practice. And I move on. So if I give you a data set, X and Y, which is precisely what this is, can you calculate what Y will be when X equals 4.5? There is no 4.5 here, right? In the data set, X is 4, it's 5. So 4.5, you use basically fit a linear regression line through this, a least squares line through this, and find Y using that line. And so first we need to make sure the data is linear. And does this look linear? No, it's non-linear. You can probably fit a line through here, but it's going to perform very poorly, especially when you want to extrapolate. So like I said, linear regression correlation coefficient doesn't apply when your data is non-linear, but we're going to fit a straight line all the same and see what the correlation coefficient will look like, even though it's not meaningful. So we fit a line through it, and correlation coefficient is 0.88, which is still looking okay, but not good enough. And it will be a lot worse when you extrapolate, which is why using correlation coefficient is not a good idea for non-linear data sets. So let's plot the line together with the data set as before. And this is what you get. A straight line looks this way, and this is curving away. So not a good idea. What do? Are we going to be stuck to using straight line no matter what? Interestingly, you can still use a straight line and get a good result from this, but you have to transform either the X or the Y axis or both of them. And in this case, we're going to transform the Y axis and see if we're going to get a straight line. So before doing that, I'm showing the results of your estimate if you use this straight line to predict. So that's what this is. Use the slope you got and the intercept and multiply by X, which is set to 4.5, and you get 2.15. Now let's move on to do the transformation. I said we were going to transform Y. So transform Y by taking a natural logarithm. So you're using numpy.log, which is natural logarithm. If you want log to base 10, you do np.log log 10. So this is just the natural logarithm of y. And you store that in z, and you can display the data frame now with z in it. And that's your log transformation of y. And now we can do a scatter plot of log of y against x, because z is log of y, and this is what it looks like. Does it look linear? Yes. So we have effectively linearized the model by taking the natural logarithm of the y-axis. And we can get the equation of the straight line. First, we do linear regression using scipy.stats. We get the slope, intercept, and R value is now 99.34%. Previously, it was 88%. So after the transformation, we are able to use linear regression and have a high correlation coefficient. We can plot that line you get using the slope and intercept, and this is what it looks like. And that is the equation of the straight line. So we can use this to predict y, but you're actually not going to be getting y, right? Because your y is your z. So you're getting z, and we already know that z is the natural logarithm of y. So we need to find y by taking the exponent of z, right? Because exponent of natural logarithm of y will give you y. E raised to power ln x is x. And that's basically what we do here. So we first use the equation of the slope and intercept to get z, which is natural logarithm of y, and we take the exponent of that to get y. And the correct value is actually 0.94 when x is 4.5. And that's it for this lab. Feel free to ask questions in the forum. I'll answer. And very soon I'm going to open up your lab, but I needed to walk you through this before you get to work on the lab workbook.